biggest situation, since I'm supposed to announce my own mini course, I probably should start with some disclaimers. You know, when it became clear that there is not much of a chance with outside speakers, I volunteered to speak about something that I'm personally very interested in. But also because of that, I don't quite know, right? I like this topic, quadrant orbits, and especially recently infinite dimensional quadrant orbits. I was doing it for many, many years, and right now I have an active project in this field. So I find this very, very exciting and interesting. But you know, it's a little bit of an improvised mini course, so we'll see how it goes. So the quality is not 100% assured. And also, like, I should also apologize, my factors in the formulas, sines, 2 pi's, and so on, well, we'll see. I'm not so sure about them. So let's see whether the camera will cooperate. I would like still to start on the right blackboard, but we'll see how it goes. Well, camera, thank you. Thank you, camera. And so I'd like to start with some brief introduction and the outline of the course. In principle, this mini course is about interaction of several fields of mathematics, and on Friday it will also touch upon physics in some way. But the big fields in math which are involved are geometry and algebra. And here on the geometric side and on the algebraic side, there are the following objects which play the major part. So on the algebraic side, we'll be looking at representations of groups. And on the geometric side, we'll be looking at Coadjoint orbits. One should probably say that interaction between representation theory and geometry, by now it's a huge field. So Coadjoint orbits, that's probably the first or the oldest tool which exists in this direction. By now there are many, many more tools, but we'll focus on that tool. So there is a link between geometric objects and algebraic objects. But maybe more concretely, Coadjoint orbits, they have a rich geometry, and we'll be focusing on what is called orbital integrals. So this is a particular aspect of Coadjoint orbits, and here for representations, we'll also be focusing on some particular topic, which is characters. So, and there is famously a link that I will probably explain today, link between orbital integrals and characters. Now, there is a technique or a topic or a theory which is called localization. And localization in this scheme of things is a tool for computing orbital integrals. In fact, it's also a tool for computing characters, but I probably don't plan to discuss it in this mini course. Now let me add to it, perhaps just to orient ourselves, the list of examples that we'll be focusing on, and may have your feedback here. It's still okay on this board. So you see the upper board and the lower board. Okay. So the main examples that we're going to look at first in the finite dimensional case. So the examples of groups will be SU2 and SL2R, and then to some extent, as time permits, the Heisenberg group, and then our main and basically the only example we will be able to consider on the infinite dimensional side. So that's the central extension of diffeomorphism of the circle, and the complexification of the corresponding Lie algebra is the Virasoro Lie algebra. And actually, that's the link how is it? Is it still visible or it becomes too low? Okay, so that's the link to the third field. So here we have this geometry and algebra, and here it is mathematical physics, or maybe just physics, both condensed matter and whatever, two-dimensional gravity, strings. So actually this topic was recently, or is still very, very active on the physics side, and that's one of the motivations to maybe go back to the theory of coadjoint orbits, which is an old and well-established theory, and to see to what extent in the infinite dimensional case it works, or what one can say about it. So in principle, the plan is that on Friday, towards the end of the mini course, we start discussing things here, even though, again, a disclaimer, I'm not sure to what extent I am competent to discuss it, but well, at least I'll try to mumble some words which correspond to my relatively poor understanding of the topic. All right, so that's the plan. And with this, maybe we jump directly into the definition and properties of coadjoint orbits. Camera. Thank you. Well, all right, let's say paragraph 1. Coadjoint orbits. Well, I guess probably many of you know very well what coadjoint orbits are, but let me still start from the beginning and give you a setup. So let's say G is a connected Lie group, and this curly G is a Lie algebra. Let me recall that the Lie algebra comes equipped with the adjoint representation of G. So capital Ad, it's a map from G to endomorphisms of small g. And the Lie algebra comes also equipped with the adjoint representation on the same space. And here let me write a formula for the apparatus of the adjoint representation. That's just the Lie bracket. Maybe notation-wise, you know, I have a preference for this matrix type notation. So for the operator adjoint G, where G is a group element, I will be saying that it maps Y to G, Y, G minus 1. So this notation is not completely standard, but it would be correct if G were a matrix group and small g were a matrix Lie algebra, and we'll use it nevertheless in the general case. So now we can move to the coadjoint action and coadjoint representation. Now, of course, we will be acting on the dual space to the Lie algebra. maybe what I should say, that everything I will be doing here, I can of course do it over different fields, but I prefer to do it over R. And when I do it over C, I'll tell you. Sometimes I need things over C, and I don't think I'll be doing it over different fields in this mini course. Right. So so for the coadjoint action, now it's defined in the following way. So the coadjoint action of the element G on the element psi of the dual space paired with Y is equal to biduality. And here I think to have the representation property, we should add the inverse. Right. So that's the formal definition of the coadjoint action. And of course, we'll see not many, but we'll see some interesting examples very soon. But for now, maybe just to fix notation. So coadjoint orbits are, of course, orbits of the coadjoint action. So an orbit passing through an element psi is just whatever you get by acting by the group G on it. And it will be convenient to introduce a special notation for stabilizer subgroups. So, so these are elements of G such that the coadjoint action preserves the point psi. So that's the stabilizer subgroup of psi. That, of course, you can do for any action, but we'll be interested in that for the coadjoint action. Now, of psi is isomorphic to the quotient, to the homogeneous space. And sometimes it is convenient to introduce a canonical projection. So the group itself projects to every homogeneous space, and in particular, it projects to every coadjoint orbit. Maybe just to write an explicit formula for how it works. So you take a group element and you map it to the image of psi under the coadjoint action. And let me denote this guy by eta. So eta is now an arbitrary point of psi. So I start with psi, I move by this action through the orbit, and I obtain every point on the orbit in this way. Okay, so now I would like to state and actually partially prove a big theorem. So actually, why coadjoint orbits, right? I mean, groups act on many spaces, manifolds, and so on. What's special about coadjoint orbits? Let me just grab more chalk. No? Camera? Thank you. Good. So the theorem, in fact, in the mini course, I don't plan to prove that many things, but I thought probably I should start by proving at least something. So the big classical theorem, coadjoint orbits. Theorem canonical symplectic structures. Now, maybe just in case, for the word symplectic, so this means we plan to construct two forms. So this would stand for the space of two forms, such that they are closed, so the omega is equal to 0. And if you write omega in local coordinates, then those two-symmetric matrices are non-degenerate. So we'll now spend some time with a proof, but I wanted to mention that when preparing this mini course, I haven't done enough of field work, but I've done some, and so I found beautiful 3.5 proofs in Kirillov's book, which is called something like the orbit method, if I'm not mistaken. So there is a classical Kirillov's book, and it contains, three. So he says it's 3.5 proofs, and specialists may enjoy looking at those 3.5 proofs. So the proof that I'm going to present here is some kind of linear combination of some of those proofs. All right. So the proof will consist of several points, and in the first point, we are defining actually not a two form, but one form, and not on an orbit, but on the group G itself. And here, well, in line with my notation for the adjoint action, I'm using some kind of funny notation or matrix type notation for Maurer-Cartan forms. So G minus 1 GG and omega 1 GG is left invariant Maurer-Cartan form on G. And here, probably it's good to remind you how the left invariant and right invariant vector fields act on those Maurer-Cartan forms. It will take just 1 minute, but you know, it's very easy, but it's also very confusing because left invariant vector fields act on the right, and right invariant vector fields act on the left, right? So I up to now, I never met a person who would be completely fluent with this fact. So I will say that X left is the vector field which acts on the left. So in principle, one should say it's a right invariant vector field, but I prefer not to pronounce those words. So X on the left and X right X on the right, and they are both vector fields on G, and X is an element of small g. Right? So you need those vector fields. So these are right invariant ones, and these are left invariant ones. Now, when such a vector field acts, say, on that Maurer-Cartan form, so what you get? When it acts on the left, you see, it stands here instead of the differential, and you get g minus 1 xg. Or if you wish, adjoint g minus 1. And then it acts when the order of x right acts on g minus 1 dg. Well, now x stands on the other side, and we simply get x. So you see, it is a thoroughly confusing thing, but it's a left invariant Malthusian form. I act by the left invariant vector field, and that's essentially the definition, another definition of those Markov-Proton forms, this equation. And then this equation follows from the definition, because when you go from left to right, you get the adjoint action. It might be slightly confusing for you how I'm using this L and R, because I want L to act on the left and R act on the right. Sometimes people say if it's left invariant, it's L. But as I say, for many years one faces this situation when left and right, and still I don't think there is a psychologically satisfactory solution. Right, that's essentially notation. Now I would like to discuss a little bit properties of that form alpha. So what's that? Alpha is invariant under G acting on the left and G psi acting on the right. I suggest I remind you how this second statement works. And for the first statement, I'm not sure, right? In a normal mini course, I would have given you exercises. So let's say that's the first very elementary exercise. So suppose that H is in G psi, and I would like to act on the form. So I'm writing it in the following way. So this is GH minus 1 GH. Of course, G doesn't act on H. H is a constant, G is a function on the group. So you see what happens. So the form G minus 1, or maybe I just try psi H minus 1 G minus 1 dq H, right? So so this Markov-Proton form gets conjugated by H minus 1, but that's the same as the adjoint action of H minus 1. And by the rules of the game, which are still on the blackboard that we don't see at the moment, we can put it as a coadjoint action on psi. So this is minus adjoint star H psi G minus 1 dg. But now I said that H in the stabilizer group, and this means that this I is again equal to psi. So we get back our output. Right. Okay, so that's one property. Now I would like to make two more computations, which will come very handy in what follows. So let me compute iota of xl alpha and iota of xr alpha. So so this is minus iota xl, and here psi minus 1 dg. And I said that this is minus psi. And here, by our previous computation, it is this. And by the iota that we described before, it is this. And by limitation that we had, it is the pairing of eta and x with a minus sign. Of course, this is just an elementary computation. I'm putting those things together, and if we do it the same thing with xr, this will be the pairing of psi and x. Well, yeah, sorry for like doing all those boring and relatively elementary differential geometry computations. So now finally we can state something about two forms, right? So alpha was a one form. Now we define a two form, which is equal to g alpha. And this is still a two form on G. So the claim is omega is basic for G psi action on the right. And well, in basic, there are two facts. So first of all, we need to check that it is invariant for that action. But this is now trivial because alpha is invariant for the G psi action on the right, and therefore omega is also invariant because omega is just the differential of alpha. Now, so invariant is okay. Now we need to check that it is horizontal, and if you don't remember what horizontal means, so I should take some element of the Lie algebra of the stabilizer, and I should check that this guy vanishes, right? So let's see whether this guy vanishes. So we are computing the order of xr g alpha. Now, well, as usual, in those differential geometric calculations, we use the Coadjoint's magic. So Coadjoint's magic says that this is L of xr minus g iota xr, and all of this is applied to alpha. L xr of alpha is 0 because alpha was invariant. So only the second term matters. So the second term is d iota xr of alpha with a minus signs compensate, and it is d of psi x. Now both psi and x are constants. So the pairing of psi and x is a number, its Dirac differential is 0, and we are done. So we have a two form on G, which depends on psi, and this two form is basic. Now, if it is basic, this means that it says it uniquely defines a two form on the homogeneous space, which is not our Coadjoint orbit. So omega is basic. It uniquely defines a two form on outside. Now, I'm not sure. If you don't mind, I would like to denote it by the same letter. So this is of course a horrible thing, but so that's a true form, this which is defined now on the quadrant orbit. So what are its properties? Well, recall that alpha was G invariant. Maybe, well, here it's slightly inconvenient in the camera. So alpha was G invariant for the left G action. Now, of course, our original omega, which is D alpha, is also G invariant for the left G action. Now it descends, the action commutes with the G action on the orbit. So the resulting form is by construction invariant under the G action on the orbit. So this comes for free. Now omega before descent, it was not only closed, it was even exact. It was D of something, but for sure it is closed. Now, this implies that that form, the descent, is also closed. It doesn't need to be exact because maybe alpha does not descend, and usually alpha does not descend. But the closeness remains. So the omega is automatic. But maybe not exact. Finally, the property that probably I'm not going to prove. I'll give you a little bit more tools to prove it as an exercise. It turns out that omega is not a decaying rate. So, as I say, perhaps I prefer not to prove it, but instead I would like to derive two more properties of omega, and these properties will be useful for us in what follows. Well, the first computation I want to do is to compute its contraction with the vector field of the Lie algebra element X. And in fact, I can do it on the orbit, or I can do it upstairs on the group. So this is on the orbit, or I can compute it on the group. It starts getting slightly confusing because I use the same notation and I identify the forms on the orbit and on the group, the basic forms. But so let's try. We've basically done a similar computation before. So this is iota XL d alpha. Now you see we played it with the right action. We can now play it with the left action. So again, Toscan magic says this is the Lie derivative of XL minus d iota XL alpha. Now the form is left invariant, so the Lie derivative again does not contribute. And we actually computed this iota XL alpha. This was the pairing of eta and x with a minus sign. So we get this beautiful answer. D of the pairing of eta, the point on the orbit, and x. And this is what is usually called the moment map equation. So it will be important for us later, but at the moment we just see that this is the direct consequence of our formulas. So it satisfies the moment map equation. And I would like to show you one more formula. Perhaps I'll leave it also as an exercise. So that's the famous Kirillov Pastan Suryo formula for AKS. And this formula says that if you compute this form at the point eta on the two vector fields corresponding to the Lie algebra elements x and y, the answer is the pairing of eta with Lie bracket of x and y. So that's a very, very famous formula. You can, of course, relatively easily derive it from our previous computations. So here we inserted one vector field x. Now we need to insert one more vector field y. So that will give us that result. And on the other hand, it gives you a key to determine non-degeneracy. So the exercise prove non-degeneracy. And to prove non-degeneracy, you need to show the following. You need to show that the kernel of omega eta, which would mean, for instance, all the axes for which the form vanishes for all y's exactly coincides with the Lie algebra of the stabilizer group. So that's from this formula. That's relatively easy to see, and I suggest to leave it as an exercise. So as I said, we partially prove this theorem, and in principle, that's a big thing, this theorem. So coadjoint orbits are special among orbits of different actions because they canonically carry symplectic structures. And we'll see at the next hour that those symplectic structures help us link this geometry to representation theory. Now I would like to finish this hour, and I don't quite know what the schedule is. In my mind, I still have maybe like 10 minutes plus epsilon, and then we make a break, or 10 minutes. I don't know, but it's fine for the audience. Of course, they cannot quite voice it, but through the chat. But I would like to finish this relatively abstract and somewhat tedious hour with some examples. Right, so some simple examples. Well, hopefully simple examples. Maybe I should say that the target of having all those examples is to better understand the infinite dimensional case on Friday. And so that's why we need to have several finite dimensional examples, which are all easy, but which have somewhat different properties. Camera, please. Oh, wow, yeah, it's cooperative. So the first example is a group of unitary 2x2 matrices of determinant 1. So the group SU2. So, and the space G star is isomorphic to the vector space R3. So it's all, one can visualize all that. So we have this three-dimensional space with Cartesian coordinates, and then coadjoint orbits famously the point at the origin, and then spheres of radius r. Now, of course, those spheres, they are supposed to carry canonical symplectic structures. What are those symplectic structures? I'll give you two descriptions. The first description is scaled by 1 over r of the Euclidean area form. So that's not exactly the Euclidean area form, but we should divide it by r. In particular, if you define the volume of this sphere with respect to the symplectic form omega r, you will get the Euclidean volume divided by r. So somewhat counterintuitively or surprisingly, symplectic volume is 4 pi r instead of 4 pi r square in Euclidean geometry. Now, the second description that I want to give you, so let me introduce the polar angle phi of rotation around the z-axis, and let me define a two-form sigma, which is dz dash d phi. So that's a two-form on the pole of R3. It's singular on the z-axis, right? So it's a two-form where it is smooth, it is visibly closed, but it has a singularity on the z-axis. So it turns out that omega r is equal to the restriction of sigma to the sphere S to R. You know, I said it's singular, but the singularity will magically disappear when you restrict. Maybe one more point. So for S to R, the stabilizers are all isomorphic to the circle. So that's also one thing that we typically want to know about orbits is the stabilizer. So stabilizer in the two forms, maybe sometimes the volume. So these are these three signatures that we would like to focus on, and here they are. Of course, for the point, the stabilizer is equal to the focal. So that's our first example. The second example that I would like to give to you is the case of SL2R. And SL2R is also a three-dimensional simple Lie algebra, but the structure of coadjoint orbits is significantly more interesting. So G star is again isomorphic to R3. I'll introduce some coordinate system X, Y, and Z, and maybe I do a picture. So quadrant orbits will be connected components of surfaces where the function x squared plus y squared minus z squared is fixed. So you look at level surfaces of the function x squared plus y squared minus z squared equals c. And almost in all cases, quadrant orbits are connected components, with one exception that I will now draw. So what are the surfaces of constant C? First of all, there is a cone or two opposite cones of C equals 0. And then there is a family of hyperboloids with two connected components inside the cone and with one connected component outside the cone. I was practicing for some time to draw this picture. I'm not convinced how is it? Is it any comprehensible? A little bit. It's a little bit comprehensible. So thank you. You're very kind. I realize how imperfect it is. So now, let's start maybe with C bigger than 0. Then what I should tell you now. So these are the orbits of what? What kind of representative I should give you? And what is nice about both SU2 and SL2R, you can identify G and G star. So that's the case of all semi-simple Lie algebras. So in principle, I can tell you what element of G I have in mind to tell you what kind of quadjoint orbit I'm looking at. So that's a particular property of the case when there is such an isomorphism. So that's why I'm just writing psi as if it were an element of SL2R. And here I would choose something like this. So a diagonal matrix of trace 0. And the stabilizer group will be isomorphic to R star. And in principle, I can even picture this R star as something like this. So that's a subgroup of SL2R, which stabilizes that element. So we can picture it somewhere maybe here. Now, what happens if C is smaller than 0? Then psi will be something like this. And the stabilizer group will be isomorphic to S1. And this S1, this is the group of rotations. Theta is of the circle. So that we can picture, for instance, somewhere here. Finally, what happens with the cone? In fact, that's here that my statement about connected components is somewhat wrong. And in fact, what happens is the following story. So C equals 0. So there are actually 3 orbits. So that's the open cone upstairs, the open cone downstairs, and the origin itself. So here, of course, the stabilizer is equal to SL2R. And here, the typical point would be the nilpotent matrix 0, 1, 0, 0. So the stabilizer will be isomorphic to R, and this will be something. This will be just the Jordan blocks just a question for you to think about. So what's going to be typical or whatever? What should I choose as a representative on the other part of the cone? So this will be a different orbit, but what should I put here? So let me finish this the description of the two forms. And the description of the two forms, fortunately for us, it's just the same as the second description I gave you in the SU2 case. So I again take sigma, which is dz wedge d phi. That's again a singular two form, which is closed weight smooth on R3. And omega is equal to restriction of sigma to the orbit, whatever the orbit is. All right, I think that's a great moment to stop. Let's have a 10 minutes break, and then we come back with more quadrant orbits and more stuff. Well, okay, that's why you need the public, right? Thanks a lot. Yeah, thanks a lot.